Okay, so it's time to make a review of some of the many wonderful kinds of categories of functors from C to set. Now, what do I mean by that? I mean, if we pick some small category C, as in some category where we can consider the objects and the arrows as forming sets. So some C, for example, it might be this one, or it might be this one, or it might be this one, or all sorts of different options we might have for a category C. Well, if we pick such a thing, we can consider this category here, which is the category which has as objects, it has functors from C to set, and as arrows, it has natural transformations between those functors. Now, the majority of this video is focusing on sort of what things look like in set to the power of C for a sort of general C, and also this kind of special case of the category of functions, which is the case where C is equal to this category that has a single arrow S from E to V plus identity arrows, okay? But there are so many other interesting cases of these type of functors. But there are so many other interesting cases of these kind of categories of functors from C to set. And so I thought I would just quickly go over a few different kind of interesting cases that we can get by picking different categories C. Now, I'm really just going to focus on what the kind of objects look like, how we can visualize them. You can work out the natural transformations and pretty much everything else you'd want to know from the different results in this video, really, because I'm really focusing mostly in this video on giving you the kind of computational tools to be able to work out how things like limits, co-limits, logical operations, exponential objects, etc. Can be calculated in general in set to the power of C. So the sort of reason for this part of the video then is to give you a lot of different examples that you can get at. So, okay, let's go then. What about if this category C here is this sort of simplest non-empty category, the category that just has one object and the only arrow is the identity arrow? Well, in that case, set to the power of C basically just looks like set. Okay. Well, what about if it's this kind of category? What about if our category C just consists of two objects which just have identity arrows and we have no other arrows? Well, in that case, set to the power of C is also called set squared. It looks like the kind of categorical product of the category set with the category set. I think it also looks like this kind of slice category we get by taking set and slicing it over a two-element set, but that ought to be checked. So basically in this category, the objects just look like pairs of sets, because basically an object in this category is a functor from this category to set. So you see A is going to get sent to some set and B is going to get sent to some set. So there we have it. Now, this is a fairly interesting category. If memory serves, it doesn't have this kind of Boolean logic where things are only just true or false. There's like more that can happen here. But on the other hand, it is basically possible to calculate most things in this category, how exponential objects work, how all these different limits and co-limits work, and so on. So it's a nice category to study, and it is the source of some kind of counterexamples because it's kind of one of the simplest categories that doesn't really look like set in some senses. Okay, so here's another very interesting category. The category set to the power of C, when we pick C to be this kind of thing, this so-called additive monoid of natural numbers. If we do this, then this category set to the power of C, we call this the category of dynamical systems. Now, I've already discussed this in my video on graphs and dynamical systems. So basically this category C, it has a single object that we call star. We have the identity arrow of star, and we also have this arrow sigma, and we could say this is the kind of free monoid generated by sigma, because the other arrows are just sigma squared, which is sigma after sigma, then sigma cubed, sigma after sigma after sigma, and so on. And they're all there as well, but we don't sort of identify them with anything. We just have this kind of arbitrary string of extra sigmas attached to extra arrows. But they're all sort of generated and sort of controlled by the original sigma arrow. Now, what does this category look like? Well, basically, the important thing is this sigma. And so a object in set to the power of C, where C is like this, it's this additive monoid of natural numbers. An object of set to the power of C is obviously going to be a functor from this category into set. So basically, it's going to map object star to some set, and it's going to map sigma to some arrow which goes from x of star to x of star. In other words, it's going to be a kind of endo function of x of star. And then all the kind of iterates of this endo function are going to be the kind of images of sigma squared, sigma cubed, and so on. So basically what x looks like then is pretty simple. It's just basically going to look like a set of states. Okay, so this kind of set x of star, we can think of it as a set of states. And then this kind of function, x of sigma, we can think of this as a kind of update function. So all it's doing is associating every state with a kind of next state. And so all we do is we just have a load of states. We have an arrow pointing out of every state to some other state. That's a dynamical system. Dynamical systems constitute objects in this category of dynamical systems. And sometimes it's also called a category of evolving sets. Now, this is an interesting category. Lots of things can be studied about it. It's a very, very sort of, I think it's a rich category from a sort of, how to say, maybe it sounds a bit pompous, but to say sort of from a standpoint of philosophical interest. I mean, it's remarkable, for example, how the sub-object classifier in this category has a particular form it does, which seems so appropriate for this kind of category of dynamical systems. Although obviously all this stuff just comes about naturally through, the interactions of things in category theory. It's really remarkable. Also, the exponential objects are interesting because sometimes for finite objects one can get infinite exponential objects. So it's sort of interesting and complicated in some sense. But, most things apart from exponential objects in this category are pretty easy to study, so it's well worth having a look at. Then there are various kind of simpler versions of the category of dynamical systems in some sense. So here's a case where we have this kind of monoid, we have this category of one object, star. Obviously, we have the identity arrow of star in this category C. But the other thing in this category C is this arrow E from star to itself. And then if we make the kind of constraint that E after E should equal E, instead of sort of allowing this kind of infinite family of iterates, as we did up here, here instead, if we just suppose that E after E equals E, in other words, like the fancy way to say this is that E is idempotent. So if we do this, then we have this kind of situation here. So in this case, we could call set to the power of C the category of idempotent dynamical systems. And then an object of this kind of category would look something like this. It involves basically a function x of sigma from a set X of star to itself, which has the property that if we sort of apply this function twice, it's the same as applying it once. So what that essentially means is that if we sort of draw out this update function, then, you know, everything goes to a fixed point within one step. Okay, so we have these states that are fixed points, and every state is a fixed point or is going to get updated to become a fixed point. So it's these special kind of dynamical systems which constitute the objects of this kind of category of idempotent dynamical systems, which is set to the power of C, where C is this kind of category where E after E equals E. We can have a similar kind of category where instead of saying E after E equals E, we insist that E after E is the identity. And then we have the so-called category of involutions. And in that case, the sort of dynamical systems, the objects essentially look like kind of mixtures of fixed points and two cycles, kind of combinations of fixed points and two cycles constitute the objects of that kind of category of involutions. Okay, so other things then. This is rather an interesting sort of category here. This free monoid with two generators. So it's hard to draw out this full category because it's infinite, but it has just one object called star, and we have the identity arrow of star, and we also have this arrow sigma from this object star to itself, and this arrow mu from this object star to itself, and then any kind of arrow we can get by composing combinations of these together. For example, sigma, 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 mu, 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 sigma, mu, that kind of composition will also be an arrow in here, and so on. Okay, so that's why it's called the free monoid with two generators, the generators being sigma and mu. And now, if this is C, then set to the power of C, we can think of this as the category of two evolving sets. So the important things really are these arrow, sigma and mu. And then when we consider an object of set to the power of C in this case, it's obviously thought of as a functor, X from C to set. Now it's going to associate this object star with a set, and it's going to associate sigma with some kind of update function. I should have called that X of sigma, and it's going to send mu to some update function X of mu. And the way we can visualize such an object is like this. Okay, we have a set of states, and then we have a sort of sigma update function assigning each state to another state, and also a kind of mu update function assigning each state to another state. So it's pretty interesting, really. I mean, it's sort of, for example, if you have a marriage, say you had a couple of people that always stayed together and they always decided on actions to do. Well, in any particular state, there'd be something that the red member of the marriage wanted to do, let's say the woman, and there'd be something that the man, the blue member of the marriage wanted to do. So then there'd be two possible ways for that couple to update their state from any given situation. And which actual one gets applied would be a matter of, discussion or whatever. So it's this kind of idea where you have a system that's not really like a dynamical system exactly. It's not deterministic, but there are sort of two different updates that can happen, and it's a matter of choice. Now, I also think there's some interesting kind of parallels with this idea and things like chess, for example. So, I mean, in chess, given any chess position, there's a way it can be updated when white makes a move. There's a sort of best move for white and there's a best move for black. So, if we think of these different states as chess positions, then we could have the red arrow being how that position might change when, if that position's obtained when it's black's move, and black does their best move, or alternatively, if white does their best move. Actually, it's a bit fuzzy for the idea of chess because in certain positions, one player might not be allowed to move. But anyway, there's definitely some interesting sorts of relationships between these kind of systems and some of the kind of ideas that pop up in consideration of things like game theory. Anyway, here's another kind of interesting system, which just involves a sort of monoid, so it just involves a category with one object called star. And here, again, we have the identity arrow, we have this arrow sigma and this arrow mu, but now we suppose that mu after sigma equals sigma after mu equals the identity arrow. So this is called the monoid of additive integers. And the basic idea is that, yes, we have these two different arrows from star to itself, but we're sort of insisting that they are inverses to one another. And so a kind of example, so if we have this kind of thing, then we can think of set to the power of c in this kind of case as having this kind of, as being this kind of category of two evolving sets where one update operation is the inverse to the other update operation. So a kind of object in this category would constitute a functor from C to set, of course. And what would that look like? Well, this object star would be associated with some set, x of star, and this arrow mu would get sent to a set, would get sent to a function x of mu, and this arrow sigma would get sent to a function x of sigma. And then these two functions would be sort of inverses to one another. So they're both functions from x of star to x of star, but one would be the inverse of the other. So when we sort of make a picture of an object like this, we'd consider it again as a set of states with some kind of update function, but that update function would just have everything cycling, like the red one, let's say, and then the blue one would just be the kind of inverse one where all the arrows go in the opposite direction. So, okay, here's another example of one of these categories of functors from C to set. This is the case where we pick C to be this category here, where we just have two objects, E and V, and these two kind of parallel arrows, S and T, from E to V. And we've already discussed this. This is this category of graphs. So in this case, set to the power of C is this category of graphs, and a kind of typical object in this, well, it's just going to be a functor from this category C to set. So E would get sent to a set, V would get sent to a set. This arrow S from E to V gets sent to a kind of function x of S, which associates each edge with a source vertex. This arrow T here gets sent under our functor x to this function x of t, which associates each vertex, which associates each edge with a source, with And so then this arrow t from e to v gets sent to this function x of t, which associates each edge, each member of x of e, with some target vertex, member of x of v. And so this kind of system pictured here, this functor x from C to set, is pictured as this kind of graph here. So notice these members of this set are edges and their sources and targets are as specified by x of s and x of t. Here's another kind of interesting example. This is the case where we pick C to be the category generated by these arrows here, an arrow alpha from A to B and an arrow beta from B to A. So in some ways this is kind of similar to some of our So in some ways, this is kind of similar to our sort of additive monoid of natural numbers. Because, I mean, the basic idea is that once we have these arrows alpha and beta, we also have all the kind of iterates of them present. So we also have this arrow alpha after alpha, and beta after alpha, and all these different kind of things we can get by iterating these kind of arrows, all these basic kind of strings of alternating alphas and betas. But anyway, like, the important thing that really specifies one of these kind of objects in set to the power of c is like how these arrows alpha and beta are going to get mapped under a functor x from C to set. And you see, basically we can think of a functor x from C to set. It's going to send this object capital A to a set x of A. It's going to send B to a set x of B. And then this arrow alpha is going to get sent to a sort of function x of alpha, and that's going to associate every sort of element of x of A. I'm drawing such elements as solid dots here. Each of those is going to get associated with some elements of x of B, which I'm drawing as sort of hollow dots here, which is obtained by updating it. So notice that there's a kind of update arrow, which is sending every solid dot to some hollow dot. And that's basically what x of alpha is. And then x of beta is sending every hollow dot to some solid dot. So, I mean, if you think about some kind of a deterministic game between two different sort of robots, when the game's in state 1, the blue robot always does something to move the system into state A, and then the red robot always does something to move the system into state 2, and then, you know, so on and so forth. Eventually the system will end up getting into a cycle because what the robots do is always deterministic. So this is the kind of outcome we get. And so in this case, basically set to the power of c is really this kind of category of dynamical systems with these sort of alternating update functions. Here's another case I'm missing out discussion of the category of functions because so much of this video is concentrating on that. I'm just trying to give an overview of the kind of things that we're missing, really. So here's an interesting one. This is this category of bouquets with 2 layers of petals.